we have been discussing the effect of external disturbances on equilibrium. And in the previous lecture, we discussed the effect of pressure on equilibrium. We also discussed that catalyst does not affect the equilibrium constant. The effect of catalyst that we discussed is to only reduce the activation energy. We discussed that if we change the pressure at which the equilibrium is arrived at, it does not change the equilibrium constant. However, depending upon the stoichiometry of the reactants and products, the equilibrium composition may change. Today we will discuss the effect of temperature on equilibrium. The reactions can be exothermic, reactions can be endothermic. Exothermic reactions are the one in which heat is released, and endothermic reactions are the one in which the heat is absorbed. The equilibrium constant will change in a different manner when the reaction under consideration is exothermic or endothermic, in accordance with Le-Chatellier principle. And we will discuss these issues in details in today's lecture. We want to discuss the effect of temperature on equilibrium constant, and we need to look for a relation which should connect the temperature, the enthalpy and equilibrium constant. Let us see how to approach this. I will begin with a relation which I have discussed earlier, but it is important to revisit that here again, which is, if I consider the temperature derivative of G by T at constant pressure, this is equal to 1 by T into derivative of G with respect to T at constant pressure minus G by T square. Or if I write again in a simpler form, G by T at constant pressure is equal to 1 by T, and here I have this expression. Now we need to look for this. What is this equal to? G is equal to H minus Ts, and from this equation I can write G by T is equal to H by T minus S, and from dG is equal to VdP minus SdT, we have minus S is equal to dou G by dou T at constant pressure. From this we have discussed earlier. So what I will do now is, I have this expression, temperature derivative of G by T at constant pressure is equal to 1 by T variation of Gibbs energy with temperature at constant pressure minus G by T. Okay, so we have this expression, and further we got that G by T is equal to H by T, and for minus S we have got dou G by dou T at constant pressure. And from this I can write that derivative of G with respect to T at constant pressure minus G by T is equal to minus H by T. Now this can be substituted over here, and what I have now is this expression. This is Gibbs-Helmholtz equation, and if I apply to the changes, let us say I apply it to the reactions, then I have temperature derivative of delta G, let me put the standard state condition, by T at constant pressure is equal to minus delta H naught by T square. And now what I will do is, in place of delta G naught, I will write minus RT log K, because delta G naught is minus RT log K by T at constant pressure is equal to minus delta H naught by T square. T and T cancel, and I can bring R on this side. The resulting equation is delta log K by dt or dou T at constant pressure is equal to delta H naught by RT square. And I want to discuss this particular equation in details. Let us go to the slides now. Le-Chatelier principle suggests that for exothermic reactions, increased temperature should favor the reactants, and endothermic reaction, increased temperature should favor the products. That is what is experimentally observed. Because if a given reaction produces lot of heat, then when you increase the temperature, according to Le-Chatelier principle, the equilibrium should shift in such a direction so as to undo the effect of external disturbance. So equilibrium constant decreases. I will mathematically prove based upon this Van 't Hoff equation. What we did was, we took Gibbs-Helmholtz equation and we converted this to changes for the reactions and came up with this equation, and finally we derived this equation: dou log K by dou T at constant pressure is delta H naught by RT square. This is called Van 't Hoff equation. This is a very important equation, very important result. And if you look into research articles, then they, instead of reaction enthalpy, many journals you will find they write this as Van 't Hoff enthalpy, because this is an enthalpy which is calculated from the temperature dependence of equilibrium constant. So this vent of enthalpy highlights another interesting feature, that we need not determine enthalpy of a reaction just by using calorimeters or from the heats. We can actually determine the value of enthalpy of a reaction if we know how the equilibrium constant depends upon temperature. Take a look at this Van 't Hoff equation in the slide. According to this equation, if I know how log K varies with temperature, I can evaluate the value of enthalpy of reaction. The question is, how do you determine the value of equilibrium constant? Equilibrium constant determination is a different matter, because what you need is, you need the activities or concentrations or molalities of the products and reactants at equilibrium. How you determine those concentrations or molality is a different matter, because it depends on the properties of the material. One can use spectroscopic method to get a value of equilibrium constant. One can get HPLC to get a value of equilibrium constant, but there are several methods we can get the value of equilibrium constant. The point is that if we can determine equilibrium constant at different temperatures, we can get enthalpy by using Van 't Hoff equation. Let us continue our discussion on equilibrium constant dependence on temperature. We have just derived this equation, Van 't Hoff equation. So let me rewrite Van 't Hoff equation over here. According to Van 't Hoff equation, derivative of log K with respect to T at constant pressure is delta R H naught by RT square. I can write this as 1 by K dK by dt at constant pressure, of course, will be equal to delta R H naught by RT square. Now, K is a positive quantity, it cannot be negative quantity. R is a constant, and T square will depend upon what temperature is given. So, at a constant temperature, at a given temperature, T square will be a constant. So, therefore, dK by dt is proportional to the value of the enthalpy of reaction. And if the value of enthalpy of reaction is negative, that means the slope of a plot of K versus T will be negative. For example, if I plot K versus T and I get a behavior like this is a negative slope. That means in this case delta R H naught is less than 0. It is an exothermic reaction. And on the other hand, if delta R H naught is positive, endothermic reaction, in that case, these are just the approximate plots, K versus T. If the variation is like this, the slope is positive. That means I have delta R H naught which is positive, and this is endothermic reaction. Let us go to the slide. This is what I discussed, that if d log k by dt or dk by dt, whatever way you want to consider, is less than 0 or dk by dt less than 0, that means this is true for exothermic reaction. As you can see from this, negative slope means k decreases as the temperature rises. And on the other side, on the other hand, if the plot of dk by dt gives a positive slope, that means the reaction is endothermic, and positive slope means k increases as the temperature rises. And that's what I discussed in the beginning, that these observations are in accordance with the Le Chatelier principle. Let us get some more insights into delta G, delta H and T delta S. Let me write this equation delta G equal to delta H minus T delta S as minus delta G by T is equal to minus delta H by T plus delta S. I have just rearranged this equation into this form. Now, what are these? This delta S is the entropy change for the system. And if there is a thermal equilibrium between system and surrounding, and delta H is the enthalpy change for the system, for the surrounding it is going to be minus delta H, because any change for the system will be equal to minus of that change for the surrounding, as long as there is a thermal equilibrium. So therefore, let us go to slide. If this is identified as change of entropy of the system, this is identified as change of entropy of the surroundings. That means, in one sense, this minus delta R G by T represents the global entropy change. That means entropy change of the system plus entropy change of the surrounding. So there is a lot of hidden meaning into this equation. We can discuss the effect of temperature based upon this equation also, but in a qualitative manner. Let us first consider an exothermic reaction. When a reaction is exothermic, the heat is given out. If the heat is given out, that means entropy of the system decreases. And if the entropy of the system decreases, we have many times discussed that the entropy of surroundings must increase. And also, if we look at in the slide that minus delta R H by T term, if reaction is exothermic, delta H is going to be negative and overall value is going to be positive. And that is what is commented over here. For exothermic reaction, positive delta S surrounding is the driving force for the formation of products. Right? So what we have discussed is, for an exothermic reaction, the increase in entropy of the surrounding is one of the major driving force for the formation of product. And now let's go back to again slide. If we look at this surroundings part, the temperature comes in the denominator. And therefore, when you increase the temperature, the favorable contribution, increase in entropy of the surrounding, is a favorable contribution that goes down. The positive delta S surroundings, which we identified as the major driving force for the formation of products, as temperature is increased, since temperature comes in the denominator, this contribution goes down, and therefore the equilibrium should shift in the opposite direction. That means the value of equilibrium constant must go down. Now let us discuss for endothermic reaction. Endothermic reaction means heat is absorbed, and if heat is absorbed, obviously the entropy of the system will increase. The delta S for the system will be positive, and that is what is commented over here. That is, for endothermic reaction, the principal driving force is positive delta S of the system. And in the same way, if we now look at the surroundings part, if delta H is positive, then this minus delta H by T term is negative. Once again, if delta H is positive, then minus delta H by T is negative quantity. That means there is an unfavorable contribution from entropy change in the surrounding. And as temperature is increased, this unfavorable contribution goes down, and that drives the formation of more products. So we found that in case of exothermic reaction, delta S surrounding is the major driving force. In case of endothermic reaction, delta S surrounding is an unfavorable contribution, and this unfavorable contribution goes down when the temperature is increased. Therefore, as commented in the next sentence, in both the cases, minus delta RH by T is the main factor deciding the shift in equilibrium. So qualitatively, we have discussed that how the entropy change in the system and entropy change in the surroundings are linked with the equilibrium or equilibrium constant, and how the temperature effect can be explained. Let us discuss more about the enthalpy of reaction from temperature dependence of K and Van 't Hoff equation. We just discussed that we can determine enthalpy from temperature dependence of K. A little more detail we can discuss. What we have is variation of K with temperature at constant pressure is equal to delta R H naught by RT square, and if you permit me to write like this, d log K is equal to delta R H naught by RT square into dt, and then I integrate from the limits, let us say here from K1 to K2 and T1 to T2. Then what will I get? I will get log K2 by K1 is equal to delta R H naught by R into 1 over T1 minus 1 over T2, after you solve the integral and substitute the values of T1 and T2. Okay, this is one way. Here we are assuming that enthalpy of a reaction is independent of temperature, so we are taking it out. Otherwise, we cannot ignore the heat capacity terms, and those things we will take up while solving the numerical problems. However, if the enthalpy does not change over a small temperature range, We can use this equation. If we know the value of equilibrium constant at two temperatures, we can calculate the value of delta H naught. This is one way. Then I again go back to Van 't Hoff equation, which is d log K by dt at constant pressure is equal to delta R H naught by RT square, and d log K is equal to delta R H naught by RT square dt, or if I just integrate, is minus delta H naught by RT plus a constant So what we need to do is plot log K versus 1 by T. Once you plot log K versus 1 by T, then you will have slope will be equal to minus delta R H naught by R. This is what you are going to get. Let us go back to the slides. This is one method that I discussed, that you plot log K versus 1 by T, and what we will get is, from the slope we can get delta H naught, and similarly you can do an integration within the limits and get a value of delta H naught from here. So one is from log K is equal to minus delta R H naught divided by RT, there should be R over here, and second is, if the enthalpy does not depend upon temperature for a short range, you can take it out of integral and use the two values of K. So what we discussed in this lecture is how temperature affects the equilibria. In accordance with the Le-Chatelier principle, for exothermic reaction, increased temperature favors reactants. For endothermic reaction, increased temperature favors products. That means the equilibrium constant will accordingly increase or decrease depending upon whether the reaction is endothermic or exothermic. We also discussed in a qualitative manner that what could be the possible reasons for this increase and decrease, and this we could connect with the entropy changes in the system and entropy changes in the surrounding. Then we derived the Van 't Hoff equation, which is a very important result because it allows evaluation of enthalpy of a reaction from the knowledge of equilibrium constant. We will discuss several numerical problems based upon the temperature and pressure dependence of equilibrium constant in the tutorial session. Thank you very much.